Okay, this time we're going to find the volume of a solid that's obtained by taking a graph and rotating it about the x-axis. Only in quadrant 1. We're only interested in the graph in quadrant 1. It's the region bounded by the function f of x equals the square root of x and the x-axis, with x constrained from 0 to 4. And again, we're only interested in what's happening to the function in the first quadrant. So the first step is we're going to find the points of intersection. Which points of intersection? Between the graph y equals the square root of x and x equals 0 and x equals 4, the two endpoints on the x-axis. Take y equals the square root of x and solve it for x. You get y squared equals x. Okay, we solved it for x. Now, we're going to let x equal 0 and x equal 4, our two endpoints on the interval from 0 to 4, and we're going to plug it into y squared equals x to find the y partners to those x values. X equals 0, x equals 4. Plug it in and we get y squared equals 0, which means y is equal to 0. So we have the ordered pair of point of intersection 0, 0. When x is equal to 4, we plug it into y squared equals x and solve, and we get plus or minus 2. So we get 2 points of intersection, one with y equals 2, one with y equals positive 2. We're only interested in the one that gives us a positive 2, and that's for the y value, and that's because we're only interested in the graph as it appears in the first quadrant. When y is equal to negative 2, we're not in the first quadrant. Okay, so those are our two ordered pair points of intersection. Step 2, we're going to find the sketch. Here's our y-axis. Here's our x-axis. Now, here's the point 0, the point of intersection 0, 0. The other point of intersection was 4, 2. And here's the graph. So there's our ordered pair 4, 2. And that graph, we drop down the line at x equals 2 because we're going from x equals 0 to x equals 2. And we have a little approximating rectangle here. We just chose an arbitrary location for that rectangle. We call the width delta x. Our a value is x equals 0. Our b value is x equals 2. Is it 2? No, I'm sorry. That's x equals 4. That's a typo. It should be 4. And the radius is f of x. It's the height of the it's actually the height of the function. F of x equals the square root of x. But it's going to be the radius of our disk that you're going to see in a moment. So this is a vertical disk. It doesn't look like it now, but if you took that little rectangle and you spun it around that axis, then you are going to be tracing out a radius. You're going to be tracing out a disk. So that function's y equals the square root of x. So now the area of this arbitrary face formed by when we spin this rectangle around circularly around the x-axis looks like this. This is what the solid will look like when we spin that piece. All right, it'll be a disk, the center, and a radius r, and we know the radius is f of x. Okay, so the area of that face is a equals pi r squared. So a is equal to pi times the square root of x squared, because we said the radius is the square root of x. And that means area equals pi times x. Step 4, we're going to find the volume now by integrating over the distance from x equals 0 to x equals 4, not 2, even though I wrote it wrong on the graph. So we're finding the volume of the solid that's formed when we take f of x and we rotate it about the axis, the x-axis. So the formula for this is v equals the integral from x equals a to x equals b of the area of the face dx. And that's going to give us a bunch of disks that we're going to stack together from a to b. So the volume is equal to x equals 0 to 4. See, the b value is 4, not 2. Of the area, pi times x, that we calculated in step 3, then the differential dx. So bring the pi out, find the antiderivative of x, that's x squared over 2. Evaluate it. You can pull the 2 out too in the denominator. You get 4 squared minus 0 squared. So the area is 16 halves times pi. It's 8 times pi. And those units are cube units because this is volume. So what did we really do? We took this curve and we took a little sample rectangle. We spun that thing and the entire curve. We spun it around the x-axis and we glued all these little spinning rectangles together and we formed this picture. Look at this picture. There's the graph. The x-axis is sort of coming out towards us here. There's the graph. Now when we spin it around, it has a bottom portion too. And we're located at x equals 4. And we're going to spin circularly and get this thing that's kind of like a solid cone that is formed when we spin this entire graph around this x-axis. And we took an arbitrary location on the x-axis, x, and we took a little slice of our estimation, our approximation disk, and that had the radius of the function, which was the square root of x. And so the area of that disk, the face, was pi r squared. So it was pi times the square root of x squared, which just gave us pi times x. All right. So you can see that we had located the radius of the arbitrary disk, and it was the square root of x. All right. And then we took the function on the top, which was the square root of x. We spun that thing around. And essentially when we integrated, we spun it around the x-axis. When we integrated, it was like a Riemann sum thing happening. We took a whole bunch of these little infinitely many faces, disks, and we stacked them all together and glued them together to get this solid of revolution. So this is a volume of the solid of revolution that we form by taking the function y equals the square root of x only in the first quadrant from x equals 0 to x equals 4 and spinning it around the x-axis. That volume is equal to 8 times pi.